How often have we experienced that a small mistake costs us a big impact in the future? Humans are always erroneous. We as humans commit small mistakes which bites us back in the future. A similar arena is cancer detection. Human error and distraction is about 94% of the cancer mislabeling errors. This happens due to mislabeling the samples, where you can see here Brenda and Linda are grouped into different packets. A claim, a recent survey claims that 66% of the lab technicians need improvement in the way they detect cancer. 28% of the patients are misdiagnosed. That's more harmful than a drug or any surgical error. Another fun fact is that MIT and ESA are working on a toilet which could detect cancer. Now that is a great example of IoT and machine learning. To give you an analogy of what mislabeling can cause, here is a short video.
This is Bob, and this is Alice. They want to diagnose for cancer. They go to a lab where they want to give their samples to a doctor. The doctor collects their blood samples and DNA samples and gives it to Trudy, an assistant. What Trudy does is misplaces the samples and then tries to analyze for their DNA for cancer. Once we have the results, that is presented for the patient. After a few months, we find that Bob dies. Unfortunately, and guess what? Alice also dies. This was because it was mislabeled that Alice has cancer and Bob does not. So therefore, Bob will not take any treatment, and therefore he dies. In case of Alice, she takes treatment, she goes to chemotherapy. Even if she doesn't have cancer, this will cause the good tissues to die, and she will eventually die as well.
This is where we come in. As a part of this course, the final project, we are taking part in the precisionFDA competition, where we are given 3 different data sets, out of which we need to derive a model which can not only detect mislabeling but can also correct the mislabeling by predicting the right values in place of the mislabeled values. Clinical data gives us information about the gender and also their microsatellite instability levels. Proteomics gives us information about their DNA and their background, race, health records, etc. And RNA dataset gives us information about the chromosome pairs, how they react to one another. Data cleaning techniques. So before we even do any machine learning, to analyze those data sets, we need to process them. Taking inspiration from Steve Jobs, who said it's the outliers, it's the misfits, it's the outstanding people who actually can change the world. Same way, we are trying to also enhance the outliers, data which won't fit into any pattern, to check if they give us any result. Now we are writing an algorithm between clinical data and proteomics data, clinical data, RNA data, and combining them to form a model. So we now have data, algorithm, and an insightful result.
So now I'm into the AWS EC2 instance. I have created my key and I'm going to select the Amazon machine image that I want. So I'm going to select the deep learning AMI Ubuntu version. So that is, I'm going to select it. I will be selecting a general purpose T2 micro, which is a free tier, and review and launch. This is my existing key pair, which I'm using, and then launch. So as you can see here, my instances are launching right now. View the launch log. Launch initiation view instance. It's already running. So now let me connect. After this is run, I'm going to open my Jupyter Notebook, which I have already done. and I've written the code. So first is to actually import the libraries, and then I need to load the test clinical data, test proteomics, test RNA, and then let us check for, this is just loading of the data. And now, as you can see here that these are test is taken on the columns and it is taken on the rows. So we can't compare and we can't relate it. So first I need to take the transpose as I've had before. And then after the transpose, I'm getting this data. Next problem is the NAA problem. So in order to remove the NAA problem, I need to run this code, which is the data.apply, which is going to replace the NAN values with the mean. And then as you can see here that, for example, we have in the column number 3, the NAN, the first testing data 1 was replaced by a mean. And then let's go forward to see the RNA from RNA sequence from we got from the sum tab 2. Let us apply random forest classifier, and we're going to fit the model. And then we're going to just extract the top 10 features. You can extract as many top features as you want, but we just extracted 10. And then we are going to display these. So these are the top 10 features, out of which I just want the first 2. We have tried the different combinations, and it seems like we have gotten better results when we take the first top 2. And now this is the reduced, it's comparison. So it just takes the columns for 360 and 364. And now we use k-means clustering on the data which is provided to us. So when we do k-means clustering, there are going to be 4 clusters which are created, and each data, which is this features, is going to fall into any one of those clusters. So when we run this, we get a plot like this, where you can see that all those clusters are evenly distributed. Some are scattered, but we have a good 4 clusters. These are the indices. We have 79 unique, applying random forest on the reduced ones. Now I'm going to group them into 4 different groups, which is A, B, C, and D. And then after it is done, I have to match the data in the clinical with the data which I obtained in which cluster. So now I'm going to refine it. I'm just going to take the MSI low, as you can see in here, for say A, the MSI low is higher than the MSI A, so I'm just going to reduce it more. I'm going to do the same thing for B, C, and D. And finally, we have got a refined output of 55.
Now going through the algorithm, the first step is replacing the NaN values with the mean values. We also tried replacing it with 0, but we got better results when we replaced them with NaN values. As we can see over here, the first in the beginning we'll import the important libraries and load the dataset. After loading the dataset, we will check the dataset. For that, as we can see over here, there are few NaN values in testing 3, testing 2, and so on for other testings as well. So in order to replace that, this is the piece of code which we will run. So as we can see, x.mean will replace all the NaN values in the dataset with mean values. It's evident over here. After that, we are going to use random forest classifier to reduce the features. We are using random forest because it gives the important features based on maximum Gini index. Now, Gini index is maximum when the distribution is normal, which means it takes all the outliers into consideration while giving us the feature importance. For that, first we will import a random forest classifier, after which we will display the top features. As we can see over here, these are the top 10 features which are the most important. I'll put the top 10 features in calls, and I will take just few which are best for the further results. So I tried taking 10 features, 20 features. I also tried taking 5, 4, 3, 2. I got best results when I took 2 features. So this is the XReduced, in which there will be just 2 features. Using that XReduced, the next step is doing k-means clustering on that. For that, as we can see over here, we'll import k-means from sklearn. We will create 4 different clusters. And as we can see, there are 4 different clusters: 0, 1, 2, and 3. So all the points are divided into all those 4 clusters, and in order to display that, we'll be doing plt.scatter. So it creates a visual of the cluster. As we can see, there are 4 different clusters represented by green, yellow, purple, and dark blue, and they are clearly sparsely distributed, which means that the clusters are properly separated. After doing that, we are going to drop the odds, which means we'll assign every cluster a majority label based on the points inside it, and we'll drop those which are in minority. For example, in green, if majority are MSI high, we'll be dropping MSI low, and so on for all the other 3. For doing that, we will append all of the indices in 4 different arrays, which would be A, B, C, and D. And then, as we can see over here, MSI high and low, and then in the end I will count the total number. So as we can see, 66 are labeled correctly, while 14 are labeled as wrong. So the next steps are checking the dropped ones for duplication and putting them in right place, which we will be doing.
We now realize that cancer is an expensive disease. A small misdiagnosed treatment can cost you around 30,000 US dollars. And in case you lose an organ because of a misdiagnosed tumor, that'll also cost you around $15,000 for lawsuits. Not to mention, it affects the mental health of the family as well. All this can be avoided by taking a second opinion, like we always do, but this time it's with a machine which runs on cloud. We are using AWS, Amazon Web Services, to run all the algorithms, which cost less than $100 to be, and so that the patients can be extra sure about it. Not to mention that the algorithm always keeps getting better. Here are some of the references. Thank you.